All right, so let's continue. Yeah, okay. All right, so I just also want to show you how it changes when we smooth, when we use, for example, the vertex normals that are provided in the file. So this one already gives normals to each vertex. So why do we still see the boundaries of these faces? So this is like a smooth cup, as you can see, but we still, although normals are computed for each vertex, we are still seeing the boundaries of these faces, right? The reason is that in this shading part, in this mesh lab, for example, there are certain options. For example, vertex, face, none. So this is basically saying which normal to use. We are currently using the face normals, which are constant throughout the face. When I change this to vertex, as you see, what happened? Geometrically, it's still the same object, but when you just click on vertex, it became a smooth cup. Okay, it looks smooth because of the shading, but if you look at the boundaries around, it's still not, in terms of geometry, it's still not smooth. Only the shading, only the coloring part became smooth. All right, if you look at its silhouette, the geometry, the coordinates are still the same. What just changes that we see this as smoothly rendered, because instead of using the face normals, we have used vertex normals, and they're interpolated. The vertex normals are calculated like this. You already calculate normals for your triangles, right? If for each triangle, for each vertex, you know which triangles are incident on this vertex. You can actually know that. For example, for each vertex, which of those triangles, how many triangles is incident on, and which triangles are these? You may know those after you compute the normals of those faces, normals of those triangles. In this case, they are quadrilaterals. For example, for this vertex, what is done is, for example, for this vertex here, it's incident on 4 faces. The face normals are computed just by using cross products. We compute the face normal for this one, compute the face normal. So 4 face normals are computed, and they're just averaged. So those 4 of them, exactly. Again, average of faces normals, exactly. Average of faces that are incident on this one. This is how those vertex normals are computed. Okay, so as you can see, it immediately turned it like as if it's like composed of a lot of triangles. So it appears really smooth. So this is good. This averaging is good for objects that are smooth like this. But what about something like this? Imagine you have a cube or some rectangular prism. Look at this vertex. It is incident on 3 faces. If you do the same thing, vertex averaging, normal vector averaging for this vertex, what will happen is that this part, it will appear smooth. It will not appear as a corner. So for certain objects, especially for certain vertices, when they're corners like this, you want to see the difference between this face and this face in terms of shading. This shouldn't be smoothed. The diffuse color from this face to this face, I don't want it smooth. So if you do the same thing for this, it will appear, unfortunately, as a smooth interpolated color around this region, which will make it look not like a cube, but something else. I mean, it will appear weird. Yeah, I mean, some kind of a. I mean, if you look from the side, it will be a normalization, interpolation of its surrounding faces. Poor man's spirit. That's a very good way to put it. Yeah, maybe yeah, it's a good. We may decide on object by object, maybe even on the same object, depending on. Maybe we can do something like this. I think it will be a good idea if the normals are too different. between the faces don't normalize because it really likes to be a corner. I mean, if in your object, if there are two faces in which the normals are facing completely different directions, it means that whoever intended to have these objects facing these different directions, probably it was a intention to make these separate faces. So based on the differences between surrounding normals, we may either, but again, this is something we should decide when we're rendering for this point on this face. For example, are you going to be using the interpolated vertex? Are you using vertex normals or face normals? Is something you need to decide for every point. Yeah, this is an interesting idea, topic actually. I haven't, probably there are solutions to this, but I haven't read any solutions to this. I'm sure there are solutions, but I'm not familiar with any of the solutions to this problem. Yeah, that we can specify some corner edges for those faces, use different kind of rendering, but for other parts, just use vertex-based normal interpolation. We can do things like that. So it's possible to solve this problem. It's not a very big problem. It can be solved by programming. Okay, so yeah, let's go over the slides now. Okay, so yeah, the triangular meshes. Any object, any complicated object like this, that's cappuccino cup, for example, could be represented, these curved surfaces could be represented by a bunch of triangles. If you have enough number of triangles, they will appear smooth. So a mesh basically is a piecewise linear. When we say piecewise linear, we are indicating the polygons here are linear surfaces. They are linear objects, and it's a combination of these linear surfaces make this curved looking object. We may have two-dimensional meshes, but we will focus on three-dimensional meshes here in this course. And smoothness may be achieved by using a larger number of smaller pieces. So this is a method, for example, to create a sphere by subdividing two tetrahedrons. So this is, one of them is called a tetrahedron. So this is maybe octahedron because it has 8 faces. So a pyramid here, another pyramid, you just put them on top of each other, you get yourself, I think, octahedron, and then you subdivide that into different pieces, and then as you increase the number of subdivisions, you are going to get yourself close to a sphere. So this is how you can achieve smoothness. A good way to have these different smooth versions is, for example, you can many real life applications actually use multiple versions of the same model, because when this object is far away from the camera, it doesn't make sense to use thousands of triangles to render the object when it's very far away from the camera, because many of these triangles are going to just project on a single pixel. There's no need to spend extra computation time for all these triangles when the object is far away from you. So there are different resolutions of models that you use. This is called multi-resolution modeling, or it's also called levels of detail. So level of detail of an object is you have different versions of it, and depending on its distance, you use a particular version, and you switch between them with respect to the distance from the camera. And the switch is really smooth because at those switching points you don't see the difference between a lower resolution version and the higher resolution version, because they appear to the viewer exactly the same when it's certain far away. Yeah, graphics quality in games is related with this. There are different ways. For example, the polygon, for example, low poly. So you might have heard this term low poly, meaning that the low polygonal version. Usually, when these models are first generated, they are probably obtained by a three-dimensional scanner or an artist, especially when it's obtained by a three-dimensional scanner. It's just a point cloud initially, and it contains, when you triangulate that point cloud into a triangular mesh, it's most of the time contains a lot of polygons. So one way to do is, for example, if you have an interesting problem, which I also worked, I think, yeah, it was my graduation project in 1998. So more than 20 years ago from now, my graduation project was related to computer graphics. If we have a very high detailed model of an object, can you produce a lower resolution of this automatically? For example, which triangles to merge to a larger triangle? So this is sometimes called decimation, and actually MeshLab has lots of algorithms for this. For example, if you go to filter, there is mesh simplification. Yeah, remeshing simplification. So this is really a quite remarkable tool, MeshLab. Implementation of lots of algorithms already here. Where is mesh simplification? Surface. Yes, simplification. Edge collapse for marching cube meshes, or clustering decimation. So it's what, and there's a tool that's saying which algorithm that it's using. For example, let's use this clustering decimation. If I do it, let's do the default one, apply. You see, now it's reduced the number of meshes. Number of vertices were like 15,000, now it's like 10,000. So now the challenge here is to, when you're doing the simplification, for example, you don't want your cup to get smaller or certain important vertices to get removed, certain important faces to get removed, but it's an interesting problem how you get different versions of this. But and also the different choices of graphics quality. For example, when you say depending on your graphics card, you may say, I want a low detailed, I want to have a higher frames per second. And probably the games are based on your selection of quality, the graphics quality. The game may choose high resolution models if you use high quality rendering, or low resolution versions if you have a low end graphics card and you don't get high FPS. You may choose a low quality version, and this is probably some games are doing this when you choose that option, they use the low polygonal models to speed up. The number of faces of an object is very much related to the computational resources that you're going to be using. So yeah, that's exactly the choices of graphics quality. Some of them are related to polygon count, for example, or some of them may be related to the details of the illumination or shading model that they use, the texture quality, texture resolution that they use, whether they use some additional special effects that are going to be applied during rendering, like fog or other things. So graphics quality is related to lots of factors, and number of polygons in a model, in a scene, is one of them. And shading effects, also shading too, and shadow effects. Shadow is really expensive, but also different shading effects are also they may be costly. For example, there you may compute shading. We are going to see two different shading models when we talk about OpenGL. For example, when we are interpolating, when we are computing a color inside of a triangle here, for example, if you're going to compute the color of a point inside the triangle. Now, do you compute the color by interpolating the normals? For example, I told you that we compute the normal vector for this point by interpolating the normals of the vertices of this triangle. What about, instead of doing that, we compute the colors of the vertices directly? We compute colors, not normals, but just run the illumination model, compute shadow and everything, reflections for the vertices, and the color inside a triangle is computed as an interpolation of the color. So you don't do any ray reflection, no shadow computation, nothing at all, no illumination model. The entire color of all of the points inside this triangle is an interpolation of these three colors. It will be much faster, right? This actually, we are going to see that's a shading model. This is called Gouraud shading. So Gouraud shading is one of the shading models in OpenGL, is actually doing exactly this. It's pre-computed colors in these. And we compute the colors for vertices, and during rasterization, it's a different algorithm. You're going to see different algorithm than ray tracing. The vertices, we'll start with vertices towards our pixels. It will be like this. Since I'm mentioning this, I'm going to quickly show you how much efficient that the other algorithm is. So the algorithm, unlike ray tracing, the algorithm works like this. For each vertex of the object, by just multiplying this vertex coordinates with a 4x4 matrix, okay, this vertex will multiply any vertex in the scene, no ray tracing at all. There are no rays. We get a vertex of the object, we multiply with a 4x4 matrix, it will immediately give us which pixel it projects onto. Okay, so this triangle you see here, its three vertices may project to these three different pixels. Okay, in the scene, and we will find this. Oops, I wasn't meant to turn off the. This default pen. Where are my annotation? It's here. I don't like this default pen. I want this pencil. So imagine this pixel here. Let me write here, and these three corners, three vertices, color 1, color 2, color 3, three vertices. By multiplying these vertices with a 4x4 matrix, we would immediately find the pixels that they're going to be projected on. So in other words, like this triangle is going to be seen as occupying this space on our image. Now, what we're going to do is, if you have computed colors for these pixels, only for these pixels, okay, the entire set of pixels inside the triangle, there will be no rays at all generated for them. The entire color of the triangle that appears on this image will be computed by an interpolation of these three colors. So this is actually 2, this is like 3. So we'll just do interpolation. This is called rasterization, we're going to see. And you can imagine now how faster it's going to be compared to ray tracing. So this is, we are going to use this algorithm. It's actually OpenGL uses this algorithm. This is the second algorithm that we will learn in this course. This is called the forward rendering pipeline, and we will learn the details of all these things, how we compute this 4x4 matrix, how it incorporates everything about the transformation of the model, about this translation. So this 4x4 matrix for this one, it will be, we'll see the details. So that's actually the second part of the course will be all about this algorithm. And that's why in early OpenGL that's why it was fast. We had real-time gaming, interactive gaming is possible due to this forward rendering algorithm. But the bad thing about this is it's not as high quality as ray traced images because of, I mean, it's very fast, it's interpolation of colors, but therefore the quality of the images are not as good as there's no shadow, because we don't produce these rays or anything. There's no shadow, there's no reflection. So if you want to get rid of these important visual clues, we use this algorithm to speed it up. But there's also, since we also want to increase the quality of our images, there are ways. You're also going to see ways to introduce shadow. Not reflection in this course, but there are some tricks, very nice tricks to increase the quality of these images which are generated by these fast methods. And this is the de facto method these practical applications, games use these days. This is the many graphics algorithms use this algorithm. Exactly, pre-baking shadows is one way to, it means that if your light sources and the objects do not change their positions, you can pre-compute the shadows beforehand, before interactive rendering, and provide them as textures. When we see texture mapping, we are going to see what this pre-baking shadows means. It basically means pre-computing the shadow and using it as an image file to map onto the models. This could be done. Okay, so but yeah, this is how we can do these things. Okay, so here is our subdivided sphere. A manifold, a surface manifold, is actually our meshes will be manifolds. It means that each edge is shared by at most two faces. So it's like a surface in which there are no degeneracies, no three faces do not face a single. There is no protruding edges out of this. So it's just think about a surface of some object. That's what a two-dimensional manifold is going to be. And there will not be separate individual vertices either. There will be connected to. So our faces, so these will not be in our models. These are non-manifold examples. An edge coming out of in the middle of a surface, or a triangle coming out of another face like this. These are non-manifolds which we are not going to deal with. Or if your object has these things, we are going to pre-process it and filter it out so it will appear like this. So this is like a valid manifold. It may appear like a surface of an object or a terrain. So a triangular mesh will be such a manifold, and we may represent it as an undirected graph with triangle faces. There are three main objects in a triangular mesh: vertices, the corners of our triangles; edges, that are the boundaries of the triangles; and faces, which are the triangles themselves. So the degree, or sometimes valence, of a vertex is the number of incident edges. And the number of incident edges is also equal to the number of triangles. Can we say that? So 1, 2, 3, 4, 5. Yeah. So it's also, so the degree of a vertex is the number of incident edges. So each vertex is incident on an edge. And a mesh is called k-regular if the degree of all vertices are k. So that's interesting. So this is not a k-regular vertex mesh, for example, because the degree of this vertex is 4, the degree of E is 5, okay, and for example the degree of J is 3, so the degrees are different. So this is not k-regular. So there are these different definitions that we're not going to discuss more actually in this course. So just like these are additional information to give you about what kind of different surfaces or object models we can have. Our surface meshes are going to be also planar graphs in which there will be no crossing edges. If there are crossing edges like this, we can actually have a vertex at this point. No two edges will cross each other. And if you look at Euler basically provided this formula for if our meshes are planar, if a mesh is a planar graph, and almost every mesh that we will be using, they will be planar graphs. There will be no holes in them. They will be simple meshes. For such graphs, our meshes will have this property, which is the number of vertices plus number of faces is equal to 2 plus number of edges. So if you put this e to the other side, it basically means that summation of number of faces and number of vertices is equal to number of edges plus 2. So it's a nice property of, even a cube has this, and this complicated object with almost 4,000 vertices and 11,000 edges, 7,700 faces also has the same property. So based on Euler formula, we can actually say that the average degree of a vertex is around 6. So 6 incident edges per vertex if we have these planar meshes. So I actually mentioned this, how we can store the mesh structure digitally. We should have the geometry of the mesh, the 3D vertex coordinate, and also the connectivity of a mesh, which vertices make up which faces. We have seen in this example, cappuccino file, that the normals, colors, texture coordinates may also be stored alongside with the geometry. And efficient algorithms on meshes, depending on why you use these meshes for rendering, for example, we may need query methods. We may need to efficiently query all vertices or all edges of a face or all incident vertices of a actually, this is, again, there is a terminology mismatch. So when two things are of the same type, vertex and vertex, for example, there it's called adjacent. So a vertex may be adjacent to another vertex, for example, if they are both sharing an edge. Okay, but incidency happens when a vertex is incident on an edge, for example, or an edge is incident on a vertex. So this is the polygon soup method, the most inefficient way to have the triangular mesh is that the one I talked about, 9 floating points per triangle, and having a single triangle table for the entire triangular mesh. So there's lots of redundancy. The vertex coordinate information for each vertex shared by multiple triangles, the vertex coordinate information is replicated again and again, 3 floats. Using a 32-bit single precision, if you use a float for these, we need 36 bytes per face. And by Euler formula, each vertex consumes about 72 bytes on average, if they have a roughly if it's a planar polygonal mesh. Now we have seen how to make this more efficient. So index face set data structure. So the name of this data structure is indexed face set. And the one we have seen was OBJ, and its format was the vertices were listed separately than the triangles. There's also this PLY format. I have an example here, my horse, PLY. As you can see, it's the PLY format. This is the ASCII one. There's also, I think, a binary version of this one. It also has some metadata. It has 5,000 vertices. Each vertex has 3 properties, which are float, x, y, z. For example, you may add additional properties, for example, property, float, nx, ny, and z. So we can pre-compute ny and z, the normal for these vertices, and list them here again, for example, as additional parameters. So each one is for a vertex, and the number of parameters, properties here list how many floats you will be listing per vertex. Okay, so let me undo these things. Okay, now we have 11,000 faces. So after these 5,000 lines, as you can see, the face information comes. Here, unlike OBJ, we don't have 3 values, so these are just triangle indices. And this first number is indicating that it's a triangle. Since it's a generic, PLY is a generic format which can also be used to represent quadrilateral meshes. It requires this parameter. Whether it's always a combination of, we may have a model in which certain parts are triangular faces, certain parts are quad faces. So this first one shows the number of vertices of this face. So it has 3 vertices and the indices of those vertices. And that's it. It's a very simple format. And since it's an efficient format, it's used by this PLY format, and OBJ use the same format. There is no vertex coordinate duplication. The coordinates are here. And we need only a total 36 bytes per vertex. So it's half of what face set structure requires. So we can make these more efficient. And regardless of the structure, the one thing that, and a very important convention is that when we are writing the triangle vertices, we give them in counterclockwise order to indicate which face of the triangle is the front face. So each triangle actually, a three-dimensional triangle in the 3D world, it has two faces, front and back. And in order to compute these normals correctly, the front-facing normals, there's a convention people use. The counterclockwise order of triangles vertices gives us its front face. So its front faces in counterclockwise order. In other words, if you were to look at this triangle from the back and read the same order of vertices like P0, P1, P2 from behind, just imagine you go behind this triangle and watch it from there, P0, P2, you will see that it will appear clockwise. Okay, or is it? Yeah, it should appear clockwise. I mean, if the same order, yeah, exactly. If you look at the same order, so this is counterclockwise from the front. If from the behind, this order is going to be clockwise order. Okay, so the front face is the counterclockwise order of vertices. And the second part, so actually we have finished the first part, how to represent objects in general. We have seen two methods, one of them inefficient, the other efficient for meshes. The inefficient one is just listing, it's called face set, it just lists each triangle separately and each vertex is duplicated here. And the more efficient version uses a vertex set and triangle set, and it saves space. It's more efficient than the other one. This is called the face set, indexed face set structure, because our triangles have now indices. Okay, so that's it for this part of this data structure for graphics. The second part, which is more interesting actually, it's more algorithmic. It's also get something from databases too. For example, KD trees are used in multidimensional databases. It doesn't need to be three-dimensional. But this quad tree, oak tree specialized for graphics. It means it's a tree with a branching factor of 8. So what's an oak tree? Okay, so oak tree is nothing but a tree with each node, each intermediate node having 8 child nodes. 1, 2, 3, 4, 5, 6, 7, 8. 7, 8. I skipped 7. So why would you have? Why would it like? Why do we need a tree with the branching factor of 8? What does it? From graphics, for example, where does this oak tree comes from? Any ideas? Why 8? It's something related to 3 dimensions. So 8 is 2 to the power 3. So, but why 2 to the power 3? Why do we use that? Let's just imagine a 3-dimensional space like this. Yeah, cube is exactly like that. This is your entire scene. Exactly. We have the entire space. We subdivide at each step. We divide our space into half in all these major axes simultaneously. So use the xy plane. For example, the xy plane divides the entire space into front and back parts. And then the front part is divided by using the xz plane, top and bottom. And there's another plane that we haven't used, the YZ plane. The YZ plane is also used simultaneously to divide the space into left and right parts. So this way, each iteration, we regularly divide our scene into regions. And that's why it's called an oak tree. And we adaptively do this division as long as there are objects. If, for example, if there are more than one triangle, more than 2 triangles or so within a region, we keep dividing that adaptively and recursively until there is a single triangle in the leaf node. So for example, if there is a big region here to the left of, for example, if the YZ plane divides our scene in such a way that the left-hand side doesn't contain any object, we are going to stop dividing at that point. And while we are traversing, so each of these regions are actually, they are strictly cubes, right? Cubical regions, in because we're always dividing by half, and when we divide it by half, we divide simultaneously. When we go down, we have 3 levels like this. When you decide to divide, you don't say, okay, I just, at this iteration, I'm just going to divide not by 8, but by 4. We don't say that. We always divide by half. So, that means that our regions, so each of these intermediate nodes here, they actually indicate a region in this 3D space, and these cubical regions, as we move down in this tree, these cubical regions get smaller and smaller, but at the highest level, when we are, for example, going to have our ray intersect with the entire scene, we only intersect our ray with these 8 the largest of these cubes, which are these 8 cubes. Okay, so we do just 8 intersections initially, and we continue recursively to lower branches only if our ray intersects with this larger region. If not, I mean, if a ray doesn't intersect with a large region, it means that it will never intersect the smaller cubes inside it. So that's the idea of this subdivision. And when we arrange our scene in an oak tree like this, it's the depth of this tree is going to be actually very small, and when we're doing the traversal, we may avoid we may filter out certain regions of the scene completely and avoid triangle ray intersection in these parts. So this is oak trees like that. There is KD tree. The idea of KD tree is, instead of dividing, so KD tree, our space isn't infinite. So it's a good question, Selim. So isn't our space infinite? For practical reasons, it will not be infinite. We will assume that it has some boundaries, min-max boundaries in all 3 major axes. It will be like in a big bounding box. Okay, so just this root node, you're right. So this root node is going to be a very large box which contains your entire scene. Actually, it makes sense, right? I mean, you may even this min-max could be found automatically by looking at the boundaries of your scene. You can find the minimum x, maximum x coordinates in your scene. You have to be careful about for example, if you have spheres, you cannot just use the center coordinate of your sphere to indicate min-maxes, because there's also the radius, right? So you have to find a bounding box for your scene, and this bounding box will be that entire large box. So our oak tree will be subdividing this large box. So that's what an oak tree is. KD tree is actually a binary tree. So actually, these are all different variations of these things. Instead of dividing each time with 8, why don't we do this in order? For example, I have a binary tree because it's easier to visualize binary trees, right? For example, what we do is, why don't we, for example, at this point, divide by the xy plane first, and at this level, yz plane, maybe then at this level, divide by xz plane. Okay, so if we alternate every time, each of these planes divide the space into 2. So if we alternate every level, so by looking at your depth, whatever level you are, or if you look at your current depth, by taking it in mode 3, you can find which is the dividing plane right now for this level. Quad trees are used, for example, also in 2D. If you have queries like this, range queries. For example, if you have a set of points and you want to, for example, have windowing queries. For example, this is my query. I want to know which of these points are inside this box quickly. So KD trees may be used for this purpose. First, so for that, for example, you first store all of your points. For example, you first divide from the median. You may sort your points by their x coordinates and also by their y coordinates. So you find the median of the points and you divide your entire space by the median. And then at the second level, you divide from the median. The division may not be equal in KD trees if you just use the median. Using the median at each level ensures that you have a balanced tree in terms of the number of points here. But there are different versions of KD trees. For example, we may have a KD tree in which we adaptively divide our scene and we don't worry about whether our tree is balanced or not. We may always divide in the middle of the space, not in the middle of the objects. Okay, so that's what KD tree may be like. We're going to talk about the details. So we're going to see these data structures, their details. I already talked about octree, KD tree roughly. I gave the overview, but we're going to see details of this bounding volume hierarchy. So this is also like an object-based method from the points of, instead of dividing the space, why don't we start from the objects? For example, this bounding volume hierarchy is something really good. For example, if an object is composed of tens of thousands of quads, like this cup here, thousands of triangles, why don't I bound this entire object inside some lower detail object, like a rectangular box? If I put a rectangular box around this, if my ray doesn't intersect with this rectangular box, I will avoid intersection with these 20,000 faces immediately. So that's what bounding volume hierarchy is about. It's a hierarchy of these bounding volumes, which are created bounding boxes. This is, the general term is bounding volume, because you may choose to bound the objects with different simple objects. For example, we can bound an object with an ellipsoid. Okay, but we haven't seen intersection of a ray with an ellipsoid, right? Maybe with a sphere. Find the smallest sphere that will encapsulate this, and instead of having six-phase cube as a six-phase rectangular box as a bounding volume, it may be the sphere. Sphere will be your bounding volume that bounds the entire set of triangles. And we're also going to use a BSP tree, binary space partitioning tree. I think it was made famous with the use of this data structure in Quake in the early 1990s, or yeah, with the first-person shooters. The way they provided the efficient real-time first-person shooters, BSP tree was a very popular data structure to speed up rendering. Okay, to filter out certain parts of the scene. So we are also going to see this binary space partitioning tree, and we are going to continue with these on Thursday. Okay, that's it from me today. I will stop recording now.